So what did the mean value theorem tell us? Yes, everything else. Well, I'll let you guys look it up in your notes, figure it out. What we're going to do here is this. But first off, what are we trying to do in integral calculus? What are we trying to do? Integrals find the area under a curve on some closed interval. The integral, the antiderivative, all that stuff is the same. All right. What we're looking at here is the way the mean value theorem works for us. Is we have some curve, some function f of x on some closed interval AB. So we're looking for the area under here. What the mean value theorem for integral calculus is telling us is this. Well, okay, first off, how do we talk about in the last couple of sections? How do we what do we discuss to find the area under this curve? What methods do we talk about? The rectangular method, remember? Find the rectangles of all these and add them all together, Riemann sum. Well, that's pretty much where we're going to start off. But instead of taking an infinite number of small rectangles, what we're going to do is we're going to find a point on the curve that's midway between A and B. And just take one big rectangle instead of taking smaller ones, we're going to take just one big one. And now take, because we're hoping at this area and approximately the same as this area. Remember, it's continuous, so it's differentiable at every point in there. So that's a possibility. So what this is saying is our function times, this is the height. F of x is the height. Remember, area is base times width, or height times width. The height of the function is the function itself. Because the height from the x-axis to the curve, that's the height of each rectangle. Now the width, since we're looking at from B to A, or A to B, this is the width. We also, as we've been discussing, the area under this curve is our function from A to B. So the mean value theorem says that there's a value C somewhere interior point of AB where it's going to give us the middle point, the average, or an intercept, really. But it's going to be mixed up in this case. So we're going to be looking at this value C here for our height. Putting these last two together, solving for our function at C, we divide both sides by B minus A. And there we have it. That is, by definition, what the mean value theorem of integral calculus is all about. Where f is a continuous function on some closed interval a, b, and C is an interior point inside AB, that this is true. That's the mean value theorem. For integrals. F is a continuous function on closed interval a, b, and there exists some value C inside a and b where this is true. Again, as always, the continuity of the function f of x is very important because if it's discontinuous, then we'll never find the average value because it just jumps up and it just ruins the average value. So let's look at an example. Show that if f is continuous, okay, if f is continuous on AB and A does not equal B, and if A to B f of x dx equals 0, then the only way that's possible is this. it the obviousness of this question is is just jumping up at us because it tells us here that A cannot equal B. So because it's a continuous function, we know that the mean value theorem has to exist. So there has to be a value C in which this is true. And we know that A does not equal B. So therefore, this can never equal 0 because A and B are different. And because it was situated, A is less than B. Whatever's on the bottom is less than the top. So the only way that this function can equal 0 well, let's work it out. If we multiply both sides by B minus A, that still equals 0. And we know that this is true. The only way this could be true is if f of x is equal to 0 at least once for any value inside there. Because a and b are not equal, they're both not 0. D of x is simply an integral factor, which variable. So that means the only way this could equal 0 is if that's 0. That's the only way, is f of x is equal to 0. Because if f of x was anything else, it wouldn't equal 0. The only way it can be done is if f of x equals 0. At least once, or everywhere. Let's look at this next one. We're using an f of x function of 9x squared minus 16x plus 4 on the interval 0 to 2. And C is some point inside our interval. You go from 0 to 2. When x is 0, y is 4. When x is 1, 9 minus 16 is negative 7, is negative 3. Thirty-six, 32 is 8. So we're looking for the area under this curve. This area here. So these are our C values, C1, C2. The mean value theorem tells us that if you're on a closed interval and the two values f of A and f of B give you two different values of signs, that means it has to cross somewhere the x-intercept. So the way we would solve this one, we have to first find C1 and C2. We would go from 0 to C1. Then we would go from C1 to C2. And then we'd go from C2 to 2. We know that this part is going to give us an area that's greater than 0. It's a positive area. This area will give us positive, and this area will give us something that's negative. Because it's below the x-axis. These bounds of integration are your x values. From 0 to C1, C1 to C2, C2 to 2. Now, since the middle part here from C1 to C2 is going to be negative, I would fix that by changing the directions of the integration. By changing the bounds of integration, I've now just changed it to a positive value. And we would add up, but we haven't discussed yet how to find each of those values yet, so we'll hold up on that. Remember, inside here, inside the integral, this f of x is really the first derivative. It's your derivative function. And we always want it to be positive on some closed interval. How do we define derivatives first? In the old days, how do we define derivatives? Using which formula? Initials are difference quotient. So what we know here is that And then what did we do? And so this is our first derivative. It's the same as that quotient, different quotient. And then what did we do? We had to take the limit as h goes to 0. So what this tells us that the derivative of our integral from a to x, f of t dt equals f of x. Example here. Remember, what's inside here is a derivative. So when we take the integral of it, we get the original function. When we get the original function, we take a derivative of it, then we're back to being the derivative of the function. It's kind of like these two cancel each other out. But very important, it's from a can be any number, to x. Has to be in that format because we're integrating with respect to t. This one has 4 examples. So here's do the first one. If y equals a to x of t cubed plus 1 dt, what does that equal? We're going from a to x of this function, it becomes f of x. So from here to here, what do we do? Yeah, anywhere you see a t, just put an x. So this one would become x cubed plus 1. Oh, right here, because we're integrating with respect to t, and it becomes x. So all we did was these cancel each other out. So f of t now becomes f of x because that's what we're going to. Yeah, because it's the derivative of the integral. So number 2. I use letters or numbers. That's B. Let's look at B. Y is equal to x to 5, 3t sine t dt. Okay, so what are you gonna do here? How do you mean?
The 5
Very good. These are in the wrong order. Kind of find Waldo. What's wrong with this picture? Okay, so if I change this to 5 to x, what else do I have to do? Whenever you change the bounds of integration, what does that do? It becomes a negative. Because look at the theorem. It has to be from a to x. So since we're from a to x, all we have to do is change anywhere you see a t to an x. So that's a negative in front. 3x sine x. And there's your answer. y equals 1 to x squared cosine t dt. What's the problem here? Yes. So because it's an x squared, let's use substitution. Remember, we're taking the, did I leave off? We're taking the derivative of these. So in order to find dy dx, and I'm using u, because this is now 1 to u cosine t dt. What's the derivative of using u? It's dy du times du dt, or dx, sorry. We got to use the chain rule. So the derivative of this function goes from 1 to u cosine t dt, that's this part, times du dt. What is du dt? Or in this case, du dx? 2x. So this part is simply the cosine u, because whatever is up here goes in place. And du dt is 2x. So it's cosine of x squared with 2x out in front. And d y is equal to 1 plus 3x squared to 4. 2 plus et dt. So the first thing we got to do is flip those two. When we do that, we got to put a negative out in front. U is 1 plus 3x squared. So when we take the derivative of it, we get negative. Leave this one as 1 over 2 plus e to the u. Now we also have to have a du dx. We have to take the derivative of this one, 6x. It's negative 6x over 2 plus e to the 1 plus 3x squared. Okay, so that was the fundamental theorem of calculus part 1. Of doing all that stuff. Now we have the second part. Which is the one we're going to use. Two. And we always start off the same way. If f is a continuous function, is continuous on our closed interval, and capital F is any antiderivative of f on that closed interval, then the integral from a to b of f of x dx is simply f of b minus f of a. This is the one we're going to be using mostly in this course. Remember, capital F is the antiderivative of f. So this is the derivative. This is the original function it came from. Because now we got to start thinking backwards. Let's look at example 3. Example 3, there is a. The integral from 0 to pi of cosine x dx. So f of x is cosine. We have to look at if this is our derivative, this is our first derivative, where did it come from? If the first derivative is cosine, where would it come from? Sine x. Integrals, we're now going backwards. We're going counterclockwise. So the integral of cosine is sine. So the way we write this is sine x from 0 to pi. What that means is we always start with the top element. So we have sine of pi minus the sine of the bottom one, sine of 0. So this one first, and then this one second. Sine of pi is 0. Sine of 0 is 0. So the answer is 0. Can you guess why? Well, you should think about that when you draw pictures. The next one, negative pi over 4 to 0. Remember, these are your x values. Your closed domain is from negative pi over 4 to 0. This is A and that's B. Our function is secant x tangent x dx. So this is what derivative gave us secant tangent? Sure. Well, how are you sure? No. Let me see. What I'm gonna do, after class, you guys are gonna come with me and I'm gonna make copies for you, all these. There, I'll give you this. Common derivatives. Look for secant tangent. Where did it come from? Secant. So these are the functions. The derivative is these. So you work backwards. So I'll make copies of this whole packet for you all. So this is secant x from negative pi over 4 to 0. So now we go to here first. So it's secant of 0 minus the secant of negative pi over 4. Remember, secant is 1 over cosine. So 1 over cosine of 0. This is 1 over cosine of negative pi over 4. Cosine of 0 is 1. Cosine of pi over 4 is square root of 2 over 2. But it's negative, so we go down. It's still in the first and fourth quadrant. Cosine is the same. No, because pi over 4, negative pi over 4, both go to the same x value, cosine. So it's always going to be positive here. So we have 1 minus this one. Take the top one, leave it alone, flip the bottom, rationalize it. So 2 radical 2 over 2, so it equals radical 2. So there's your answer.
The upper limit b is always greater than the lower limit a. For an integral, is b always greater than a?
Well, yeah, because you're reading left to right on the x axis. It's always left to right. Yes. And that's that's the reason why if it's ever backwards, you have to change it and then change the sign because it's now going backwards. C. The integral from 1 to 4 of 3/2 square root of x minus 4/x² dx. First thing I always want to do if you have radicals or rational equations is make them so they're no longer rationals or radicals. So 1 to 4, this becomes 3/2 x to the power 1/2 minus 4 times x to the power -2 dx. Okay, the general rule approach for integrals. Remember, in derivatives, we always subtracted 1. Now, if we start off with that, we have to add 1, plus we have to divide by it. So the integral of x. Okay, so that then this one is 3/2 x to the power 1/2 plus 1 over 1/2 plus 1 minus 4x to the -2 plus 1 divided by -2 plus 1 from 1 to 4. Three over 2 x to the power, this is going to be 2/2, so it's 3/2 over 3/2 x to the power -1, -1. Flip the bottom one and multiply it. That negative cancel. So it's 4/x. Those cancel. This will be x to the power 3/2 plus 4/x from 1 to 4. Any questions about what I did so far? Yes.
So this is not an equation when you use chain rule,
No, there is no chain rule. We're going backwards now. Chain rule is only for derivatives.
want to find derivative with chain rule for an equation. For example, 7x bracket x minus 30 minus 5.
No, a chain rule would be used if we had this. A function within a function.
What if you have a number in front of you, 7x for instance? Yeah. So will you get the same result with chain rule?
Are you looking for derivative or integral? Then we do a product rule, and this is a chain rule. So this would be your F, this would be your G, and for the G, you have to do the chain rule. Yes.
Okay, so example we're doing now, we have like sports. Transform. The part inside the parentheses. We'll work on how we're not finding the derivative, that will work.
Right, this is the original function. If we take the derivative of this, we'll end up with this.
That is a derivative. Okay,
This is the derivative of this. That's the way to check it. If you do this correctly, let's check it.
Right.
Let's check it. X to the power 3/2 plus 4/x. So the derivative of this one is 3/2 and minus 1 makes it 1/2. This one is 4x to the power -1. So the -1 comes down and subtract 1. 3/2 square root of x minus 4/x squared. So now as you see that's how it works. That's how you test it.
Well, right now we're using integrals to figure out how we got to the derivative.
We're using the integrals to find the area under the curve. And we just test it by taking the derivative. Take the derivative of this. If it doesn't come out with that, we did something wrong. So now, once we get to this one, we can't go any further. We did all this stuff. Now we take with x at 4. So we have 4, 3 to the power 2 plus 4/4. Minus with the bottom one. 1 to the power 3/2 plus 4/1. So 4 to the power 3/2. Remember, 4 to the power 1/2 is the same thing as square root of 4. So that becomes 2. So what we have here is 4 to the power 1/2 cubed plus 1. 1 to any power is 1 plus 4. So square root of 4 is 2. 2 cubed is 8. 8 plus 1. 1 plus 4. 9 minus 5 equals 4. That's your answer. That's the area under the curve from 1 to 4.
Looks like that. Part of the work on. Typical starts with the derivative. Figure out.
What function gave us that derivative?
Was.
Right. That's what we're in essence looking for.
And we use the bounds to figure out the area.
Yes. Always the top one minus the bottom one. Which is what our formulas, our theorem told us. Once you take the integral of f of x, we get f. Then it's b minus a. Well, actually, I should have put something between there. It should have been f of x from a to b equals this. That's the way it works. So we start off with our integral. We get our function, our antiderivative. We go from b to a. So that's what this becomes. Right. Now the integral from 0 to 1 of dx over x plus 1 So what is the antiderivative? If this is my derivative, what is my antiderivative? Where did this come from? If we wanted to, you could split it up. If you look at that, it's du over u. So which one have we used that looks like that? Mhm. ln absolute value of u. So it's ln absolute value of x plus 1. The reason we use absolute value of x plus 1, absolute value is because this can be negative. So we'll put in absolute values. This is from 0 to 1. So it's ln 1 plus 1 minus ln 0 plus 1. Now, since these can never be negative now, ln of 1 is 0. So the answer is ln of 2. Again, the apprehension in your voice. Try it. If you think it's ln 1 over this, then take a derivative of this function, see what happens. The derivative of this function would be, since ln, it's 1 over this times the derivative of this, which is 1. There it works.
Yeah, I wanted to say that, well, I guess I'm just, never mind, in my head, I was thinking it was Ellen.
But yeah, you just go with it. Just take a stab at it. Let me show you the formulas again. E. The integral of 0 to 1 of dx x squared plus 1 . So what do y'all think? What does this one look like? Okay. Let me give you this page here. The integrals. What we're looking for is what equation has 1 over x squared plus 1? Which number? 12? No. This is the integral of u to the power n. And there's no x there. So it's not 1. This one is integral of du over square root? No. How about this one? Integral of du over there you go. A squared plus u squared. This is du over u, or a squared. A is a number, or it could be a letter in this case. Well, it will say u is the x and a is a number. U is x, a is 1. So it's u squared plus a squared. So it's rule 18. Where a is 1, so the answer here is 1 over 1 inverse tangent of x over 1. So it's inverse tangent of x. It's inverse tangent of x.
Okay, the derivative of 1 all over x plus 1 without using the formula. Because,
Well, you can try, but it'll be very messy. And when I was in graduate school, we used to carry a book that was only a table of integrals and derivatives. About the same size print. It was about 1,800 pages. And we had to go through and look for these. So we know that this integral is the inverse of that is inverse tangent from 0 to 1. So 1 minus 0. So what angle of tangent gives me 1? Hmm? 45 is pi over 4. Not 45 degrees, but pi over 4. So it's pi over 4. What gives us 0? We have to be between 0 and 1. There's a sine over cosine. Sine, for this thing to be 0, what makes sine 0? 0. So it has to be within the first quadrant. So the answer is pi over 4.
Which probably like carried around the screen was like that. It's the same thing like trading, trade tables.
Mhm. Way before calculators, yeah. Which when I was in school, that's when calculators were first coming out, and they were awful. Example 4. This is dealing with the integral of a rate. We know that this becomes f of b minus f of a. Where x is between a and b. Example 4. These are just interpretations of that theorem. If c of x is the cost of producing x units, Then C prime is the marginal cost. And the integral of the marginal cost is the cost at the second price point minus cost of the first price point. Or unit constructed, sorry. This is the cost of increasing production from X1 to X2 units. If an object with position function S of t moves along a coordinate line, its velocity is the first derivative of S of the position function. Then the integral of the time 1 to time 2 of the velocity is simply t, the position function at t2 at t2 minus position function at t1. This is displacement over time, t1 to t2. And the absolute velocity is the total distance traveled. Over T1 to T2. We've talked about both of those already. It's now working backwards. We talked about marginal cost, we talked about marginal revenue, marginal profit. Now we're just working backwards. All right, let's look at an example. Consider again our analysis of a heavy rock blown straight up from the ground at dynamite. This is the rock blown straight up. The velocity of the rock at any time t during the motion is denoted by this function. Feet per second. Okay, find the displacement. over the time period from 0 to 8 seconds. And find the total distance traveled. Over that time period. So remember what displacement was. Yeah, displacement is S of T2 minus S of T1. That's displacement. So S of T2 minus S of T1, which is the integral of our velocity function. So that means we got to take our velocity function from 0 to 8. 160 minus 32t dt. Okay, this one here has a t. This one has a t, but the power is 0. Remember what you do? You have to add 1 to the exponent and divide it by the same number. So this one's going to be 160 t0 plus 1 divided by 0 plus 1. And the second one is 32t to the first. So we add 1 there, and we do the same thing on the bottom. So we have 160t minus 32t squared over 2. Thirty-two divided by 2 is 16. So we have 160 times 8 minus 16 times 8 squared minus 160 times 0 minus 16 0 squared. That all is going to be 0. Sixteen times 64. So the answer is 256. Any questions so far? Now, part 2 says find the total distance traveled. The total distance traveled was the absolute value of t. So we have to take the absolute value from 0 to 8 of the absolute value of the velocity. What we have to do here first is remember, the graph is going up and then it's coming down. So we have two different velocities. At what point is it at its highest point? So this is velocity. Velocity up is positive, down is negative. So what are the two values? It's 160 or minus 16 t squared. No, velocity is 160/32. What we have to do first is set that equal to 0. We have to find out when it reaches its top. The change happens after t equals 5 seconds. So we have to go from 0 to 5 seconds of the absolute value of t. And then we have to add from 5 to 8, the absolute value of t. Because that'll get rid of any of the discrepancy of what is positive, what is negative. Now, how is this different than if we didn't separate them? It all goes back to where this formula comes from. The Riemann sum of adding the areas under the curve. It's going to be positive one side, it's going to be negative on the other side. So we have to get rid of those. So that's going to be, since this can't be, it goes 160 minus 32t from 0 to 5, from 5 to 8. The integral of this, as we calculated, is 160t minus 16t squared. So we 160 times 5 minus 16, 5 squared. Minus 160 times 0, 16, 0 squared. That's the first part. 160 times 8. 16 times 8 squared minus 160 times 5 minus 65 squared. That's 0. The answer is 544. Again, yeah, hopefully y'all could do this, using calculators, you can do this. So any questions about what I have up here? What's example 5? Total area now. Is area ever negative? No, so it's always positive. So let's look at example 6. The graph of this function, x squared minus 4, and its mirror image. If we look at the graphs of these things, like what is this one? So if you look at both of these graphs, they're the same graph, just flipped across the x-axis. A says the definite integral, compute the following. Definite integral over -2 to 2. And area between the graph and the x-axis over -2 to 2. So for A, do the definite integral for both of these separately. See what you get. The definite integral over -2 to 2 of f of x equals -2 to 2 of x squared minus 4 dx. So what's the integral of x squared? X cubed over 3. Because you add 1 and then divide by the same number. And then minus 4, since it's a constant, you put an X behind it. This is the antiderivative. So now we start at 2. We got 2 cubed over 3 minus 4 times 2 minus negative 2 cubed over 3 minus 4 times negative 2. Eight over 3 minus 8. Negative 8 over 3 plus 8. Eight over 3 minus 8 plus 8 over 3 minus 8. 2 times 8 over 3 minus 16. 16 over 3 minus 16 over 1. We have 16 over 3 minus 48 over 3 is negative 32 over 3. And do the same thing now with the other function, the 4 minus x squared. The integral from negative 2 to 2 of g of x. Negative 2 to 2 of 4 minus x squared. Equals 4x minus x cubed over 3. Now, in case you haven't noticed already, that the integral of a constant is that constant with an x behind it. Because the first derivative of an x is whatever the coefficient is. So here we have 4 times 2 minus 2 cubed over 3 minus 4 times negative 2 minus negative 2 cubed over 3. Eight minus 8 over 3. Negative 8 minus negative 8 over 3. Plus 8. That's a plus, that's a minus. 16 minus 16 over 3. 48 over 3 minus 16 over 3 is 32 over 3. So what do you notice about those two equations? Which one's which? This one's negative because it's below the x-axis. This one's positive because it's above the x-axis. We're good. And B said the area between the graph and the x-axis over that interval. It's the area, remember, area can never be negative. So since they're both the same numbers, take the absolute value of it. The area of the two functions is 32/3. Same type of concept, but let's look at example 7. Show the function f of x equals sine x on the closed interval 0 to 2 pi. Compute A, the definite integral over 0 to 2 pi, and area between g of x or f of x and the x-axis over 0 to 2 pi. What does it mean by definite integral? What is a definite integral? What's an integral? Well, I mean, but how do we represent it mathematically? Whereas to compute this, how do we set up an integral? That symbol there is the integral symbol. It's definite because it goes from 0 to 2 pi in this case. It goes from A to B. That's a definite integral. So we're going from 0 to 2 pi of sine x dx. What's the integral of sine x? Negative what? Very good. Negative cosine x from 0 to 2 pi. We have negative cosine at 2 pi minus negative cosine at 0. Cosine of 2 pi is 1. This negative and negative becomes a positive. Cosine of 0 is 1. So the area is 0. Now, why would it mean 0? Right, because if we look at the graph from 0 sine starts here. So part of it is above and part of it low. If it equals 0, that means these two areas are equal. So what we have to do now is separate it from where it's positive, where it's negative. Find the area between there. So what do we do?
Balance from Here, find that.
So we do it from 0 to pi. And then just from pi to 2 pi. Very good. Now, where the mean value theorem is where it's the middle part, where it crosses the x-axis. We do them both separately. So it's negative cosine x from 0 to pi, negative cosine x from pi to 2 pi, negative cosine pi minus negative cosine 0, negative cosine 2 pi minus negative cosine pi. Cosine of pi is look at the unit circle.
Oh, one.
Nope. This is 0. This is pi over 2. This is pi, 3 pi over 2. What number's there? Negative 1. So equals negative 1. Negative and negative makes it a positive. Cosine of 0 is 1. So it's 1 plus 1 equals 2. Cosine of 2 pi is 1. That becomes a positive. Cosine at pi is negative 1. So it equals negative 2. Take the absolute values and add them together. We get 4, and that's our answer. Is this stuff getting kind of easy or understandable? I know I'm moving pretty quick.
Yeah.
So the definite integral is what it is. The area is, if it equals 0, then we have to break it up into its smaller constituent pieces. One more example, example 8. Find the area of the region between the x-axis and the graph of this function. From -1 to x to 2. So it says find the area. The area is determined by the closed interval from a to b of f of x dx. It goes from -1 to 2, x cubed minus x squared minus 2x. To save us time, since going from -1 to 2, that's a very large stretch. Let's see if there's any x-intercepts inside there. So let's see, let's set it equal to 0 first. X cubed minus x squared minus 2x. We can factor out an x. We have x squared minus x minus 2. That's going to be x minus 2, x plus 1. So our intercepts are at 0, 2, and -1. -1 and 2 are the endpoints, so the only one we have to worry about is that. So to save us some time, we have two areas. From -1 to 0. And then from 0 to 2. And one of those is going to be above, one is going to be below. So what's the integral of x cubed? Because you add 1, and wherever you get there, you put on the bottom. Minus the next one. Very good. Two x over 2. Anybody not see what I'm doing there? X integral of x to the n is x to the n plus 1 over n plus 1. That is the basic rule for integration. So we get 0 over 4 minus 0 over 3 minus 0 over 2 minus -1 to the 4th over 4 minus -1 cubed over 3 minus -1 squared over 2. So that's 0. -1 to the 4th is 1. 4. Negative, that's a plus 1 over 3. -1 squared is 1 times 2 makes it a 1. LCD. Minus 1. So that's 12. So this is 3 over 12 plus 4 over 12 minus 12 over 12. So -5/12 in the first one. X to the 4 over 4, x cubed over 3, 2x squared over 2, the 2's cancel. Two to the 4th over 4 minus 2 cubed over 3 minus 2 squared minus 0. 16 over 4, 8 over 3, 4 minus 4 is 0. So the answer is -8/3. Well, if we have the negative out in front, makes that a positive. This negative makes it a positive. So we have 5/12 plus 8/3. We take the absolute values of them. We multiply 4/4 to get a common denominator. So it's 37/12. That's the area. Remember, it's a cubic function, so it looks something like this. And if the intercepts are at -1, 0, and 2, this one's positive, this one's negative. And the bigger part, because it's a larger stretch, is going to be a bigger negative number. Okay, that's that one. And we'll finish up everything else tomorrow.